Okay, we're back to the second part of lecture 18, and we were looking at linear systems of differential equations. And so after we talked about the idea of diagonalizing, let's talk more about what we can do, what little we can do with nonlinear differential equations. So if autonomous first order differential equation looks like y prime is equal to f of y, and this equation has an equilibrium solution if I can find some constant where y e is equal to c, a constant vector, making the right hand side of the equation equal to 0, and making the change, the left hand side also equal to 0, because of course they should be equal. Great, so again, solving an algebraic equation instead of a differential one. So here's an example that we can look at here. So let's find all the equilibria for this first order linear system. So I really want to solve minus 2, 1, 1, minus 2, y is equal, or let's say plus 0, 3 is equal to 0, 0. So I can subtract this equation, this vector to the other side of the equation, and then multiply by the inverse of this guy, right? So ye, the equilibrium that satisfies this, is going to be the inverse of this matrix times 0 and then minus 3. So what's the inverse of that matrix? We can just do it really quickly. So it's 1 over the determinant. The determinant is minus 2 times minus 2, so 4 minus 1, so 1/3. And then I flip the diagonal entries and multiply the off diagonals by a negative sign. Great. And I don't want to have so many negative signs. So I'll say that take a negative out of here, negative out of here. So I have 1/3, 2, 1, 1, 2, 0, 3. It's easier to write. So this becomes 1 times 3 and 2 times 3, 6. So divided by 3, it's the vector 1, 2. Great. So the equilibrium for the system is 1, 2, and it has 1 equilibrium. So actually, this was not just some arbitrary nonlinear system of differential equations, but it was linear, right? It looked like ATY plus BT. So a linear system of this form is going to be homogeneous if BT is 0 and non-homogeneous otherwise. So the one we had above was non-homogeneous. So the way that we would solve these systems is a total analog to how we would do for scalar systems. So if I have this non-homogeneous first order differential equation, I can find the characteristic solution, the general solution, by just looking at the homogeneous system, and then find the particular solution by doing undetermined coefficients or variation of parameters for the non-homogeneous system. So just as a practice, let's look back at this system that we just found the equilibrium to, and let's see if we can write a general solution for this guy using this principle of superposition that we just established holds for linear non-homogeneous systems of equations, just like it did for scalar systems. Okay, so what should the characteristic solution look like? The one for the homogeneous part. So the homogeneous part looked like y prime is equal to minus 2, 1, 1, minus 2 y. How do we solve that again? Right, we find the eigenvalues and the eigenvectors, we have a linear combination thereof. So what are the eigenvalues? I have lambda plus 2 minus 1 minus 1 and lambda plus 2. What I do, lambda I minus a. So I have lambda squared plus 4 lambda plus 4 minus 1. So lambda squared plus 4 lambda plus 3, which means I have lambda plus 3 lambda plus 1 as the characteristic equation. So the eigenvalues are minus 1 and minus 3. So what are the eigenvectors? When lambda is minus 1, make sure you can see this. Move it up a bit. When lambda is minus 1, this equation becomes 1 minus 1 minus 1, 1 times some v1 is going to be the 0 vector. So the eigenvector associated with that could just be 1, 1. And when lambda is minus 3, this matrix up here becomes minus 1, minus 1, minus 1, minus 1. Meaning that v2 could be 1 minus 1. So the characteristic solution is going to be the linear combination of these. C1 e to the minus t 1, 1 plus C2 e to the minus 3t 1 minus 1. We can assume a form for yp, but we can notice that we're just adding on a constant vector. We recall that the equilibrium that we found before was 1, 2. So since this b of t is a constant in this linear form, y of t is just yc plus the equilibrium. So c1 e to the minus t1, 1 plus c2 e to the minus 3t 1 minus 1 plus 1, 2. Excellent. So the second part of this question is calculate the limit as t goes to infinity of yt. And then what do we observe here? Well, both of these exponentials decay and go to 0. So this is just going to this term, which is the equilibrium. So a solution goes to equilibrium as time goes to infinity. Excellent. Okay. So I hope that's making some sense. Let's try another example. We'll again look for equilibria and a general solution, and then try and interpret what's happening to that solution as time goes forward. So here's our next example now on page 10 of our notes. So we have a first order linear system. Now we have 3 equations rather than 2. And first we want to find all of the equilibria for this system. And we want to find a general solution and then find the solution or find a solution. So I start close enough to the 0 vector and show that the limit of that solution is going to go to infinity. Okay, so for the first part. So to find equilibria for this system. So what should we do? So we want to solve ay is equal to 0. Again, we want to solve a differential equation, an algebraic equation rather than a differential one. Okay, so before I go trying to solve this, I think that what we should see is whether or not A has a null space with anything except the 0 vector in it, right? So if the determinant of A is not equal to 0, then the only vector that can multiply it and give you a 0 is the 0 vector itself. But if the determinant, so I'll say recall, if the determinant of A is equal to 0, the null space is non-empty. What does that mean? We could have some non-trivial equilibria for Y. But if the determinant of A is non-zero, only 0 makes AX is equal to 0. True. Only, I guess, X is equal to 0 the way that I wrote it. So what about the determinant in this case? What's the determinant of A? We'll call this matrix A. Is there a row or a column with just one term? Yep, the 2, 2 position, right? So minus 2 times, so it's positive, negative, positive. The determinant of 1, 1, minus 1, 1, right? Which is minus 2 times 1 minus a minus 1. So plus 1 is minus 4 non-zero, which implies that the equilibrium is only the 0 vector. I guess we'll say origin in 3 space. Oops, move it up a little. Okay, I hope that makes sense. And if not, we can talk about it tomorrow. Okay, so part 2. Find the general solution of this guy. So to do that, we have to find eigenvalues and eigenvectors. Great. So, characteristic equation. Lambda minus 1, 4 minus 1, 0, lambda plus 2, 0, 1, 2, lambda minus 1. Again, we can do the cofactor expansion with that middle term. So I have lambda plus 2 times the determinant of lambda minus 1, minus 1, 1, lambda minus 1. So lambda plus 2 times lambda squared minus 2 lambda plus 1. And then plus, yes, it's minus and then a minus, and then plus another one. And that should be equal to 0. This guy, I don't know how to factor. Right, these sum to 2. So let's solve it using the quadratic equation. So lambda is negative b2 plus or minus the square root of b squared. 4 minus 4 times a times c, so 8 over 2. So that's going to be complex in general. So I have 2 plus or minus 2i over 2. So 1 plus or minus I. So the eigenvalues are 2, 1 plus I, and 1 minus I. And what are the eigenvectors that correspond to this? So when lambda is 2, I have 1, 4, minus 1, 0, 4, 0, 1, 2, 1. And lambda is 2. Is that right? Okay. Oh, it's not 2. It's minus 2. right? Minus 2, the factor is lambda plus 2. So when I have minus 2 here, okay, that's better. Minus 3, minus 1, and minus 3 here. Okay, great. Minus 2, no, not minus 1, sorry, 0, 0 here. Okay, so I'm going to put next here. I'll write it clearer. This matrix, lambda I minus a becomes minus 3 for minus 1, 0, 0, 0, 1, 2, minus 3. Great. Okay, and now I like this because the row sum is always equal to 0, right? So V1, in this case, if I call this lambda 1, is going to be 1, 1, 1. Awesome. Oh, can you see that? Yes. Okay. What about when I use one of the complex eigenvalues? So lambda 2 is 1 plus I. And I plug in here. I have 1 plus I minus 1. So I, 4 minus 1, 0, 3 plus I, 0, 1, 2, I times V should equal to 0. So what works here? Let's see. So first of all, the second row having a non-zero entry and then nothing to sum it with tells me that V must have a 0 for the second term. So it just has to be really in the first and the third columns. And the signs aren't exactly the same, but I know can flip the sign. So if I multiply the third column by I, I'll get I minus I here, and then 1 plus I squared, which is minus 1. So that works. So 1I works as an eigenvector. And then we know the complex conjugate eigenvalue, 1 minus I, has an eigenvector, V3, which is the complex conjugate of V2. So 1, 0, minus I. Can you see that? Yeah. Oh, it's a little bit blurry here. Move it to the center here. I'll try and make it a bit bigger. Okay. So the general solution here, y of t is going to be c1 e to the minus 2t times 1, 1, 1 plus c2 e to the 1 plus it 1, 0 I plus c3 e to the 1 minus it 1, 0 minus I. Great. No problems, right? The only issue is for the third part, I want to understand the norm of this guy as t goes to infinity. So it might be easier to write this in a complex, in a real form, right? Using Euler's. Okay, but so let's see here. I look at this as a sine and cosine. Push it up so you can see here. Is that good? Yeah. If I look at this as a sine and a cosine, so I have e to the 1 plus I t 1, 0 I. That's actually e to the t times cosine t plus I sine t plus 1, 0 I, which is like e to the t cosine t plus I sine t 0 minus sine t plus I cosine t, right? And if I add this with the complex conjugate, right? So I add this with this complex conjugate. So e to the 1 plus I t, 1, 0, I, plus e to the 1 minus I t, 1, 0, I. Can I get something that looks real? So I have e to the t from both terms, and I have cosine t plus I sine t, and minus sine t plus I cos t from this first summand. And the second summand is going to be cosine t minus I sine t. The reason for that is that cosine is an even function and sine is an odd function. So then I have plus cosine t minus I sine t. And then when I multiply by I have plus sine t plus I cosine t. Is that right? I think so. Okay. So is this guy gonna end up being real? Can I make this guy real? Let's see. Maybe we should regroup for a second. Maybe we should try not to make this real. Maybe we should look at what the problem says. The problem says, find a solution y of t such that the norm of y naught minus 0 is equal to 0.01. So what's y naught at 0? So I have C1, 1, 1, 1 plus C2, 1, 0 plus I. Oh, yes, I guess I should have done this way. We don't have to do this so much in general. Okay, so if I've got this guy and I add it up, I can find C1, C2, and C3 that makes this true, right? So this should be, what, C1 plus C2 plus C3. C1 here, and then C1 plus I, C2 minus C3. So that means we want C2 to equal C3 to get rid of the imaginary part here. Let's just call that C. So this would be C1 plus 2C, C1, and C1. So I can choose the C's in this way. So it gives me a lot of options. And I want to make it go to infinity as t goes to infinity. So that's going to actually be really easy, right? Because what I saw, let me show you this other page. So these terms look like e to the t and then a sine and a cosine, or e to the t sine minus cosine. The e to the t is going to blow up regardless, right? So the limit of the norm of y of t as t goes to infinity is going to equal infinity, since second and third summands are multiplied by e to the t. And then the rest and sines and cosine. Excuse me, they don't decay or grow. So the second part is fine, but I can choose a C1 and a C that make that norm as close as I want. So I'm going to stop that here. Choose C1 and C to get the norm of y naught minus 0 to equal what, a number, 0.1. Okay. So let's just say that that's a doable thing. Oops, sorry, there you go, that's what I wrote. Let's not get deeper into like actually doing numbers here, because that becomes a little bit painful. But hopefully it's clear that I can choose an initial condition that is in a range that I'm interested in, and this guy will go to infinity. Okay. So that example is supposed to lead us to this idea of the next theorem, which is on page 11 here, which says if I have this linear non-homogeneous system here with A being invertible, then I have a unique equilibrium here. And if all the eigenvalues of A have negative real parts, then for any solution, we're going to go to the equilibrium as t goes to infinity, and we'll call the equilibrium globally asymptotically stable. So it's like asymptotically stable because we're going to go to it as t goes to infinity, but globally because it's independent of how far away the initial condition is. It's the only equilibrium. So as you go forward in time, you're either going to go towards it or go away from it. That's the only things you can do. So global meaning for any initial condition. If you have at least one eigenvalue with a positive real part, then you will have a solution that makes this guy go to infinity. And so we'll call the equilibrium unstable. And we can see from the last example, right? The last example had some eigenvalues with negative real part, but these guys had positive real parts. So for sure this was going to be unstable. And we can easily see why that is if we look at this kind of diagonalized solution, right? This solution here for the non-homogeneous system in this case is the homogeneous part. So this is YC. That depends exactly on the signs, the real parts, the eigenvalues. And then the particular solution, which is just this equilibrium here, because we only added on a constant. So you're either going to decay where all these go to 0, and I'm just left with this, or at least one of these blows up. Those are the only options. Okay, so for this kind of simpler 2x2 system, let's look at an example of that completely. So we'll find an equilibrium, and then we'll try and understand whether or not it's globally asymptotically stable. Okay, so the system we want to look at is y prime is 0, 1, 1, 0. So what's an equilibrium? Equilibrium. So YE, we said is going to have to be 0, 1, 1, 0 inverse times 2, 1. So what's that? The inverse of this guy. The determinant is 0 minus 1, so minus 1. I flip the diagonals and I multiply by a minus 1, so this guy happens to be its own inverse. 0, 1, oops, 1, 0, multiplying 2, 1 gives me 1, 2, right? Flips the components of the vector. And so, yeah, so that should be our equilibrium. Is that right? Seems like it might should have a negative sign. I guess that looks okay. Okay. So, so let's write the solution for the system, right? Okay. Eigenvalues and eigenvectors. I7A. Lambda I minus A, and determinant going to be lambda minus 1 minus 1 lambda. Okay, so I have lambda squared minus minus another minus 1 is going to give me plus and minus 1 as our eigenvalues. Great. When lambda 1 is 1, I have that lambda I minus a is 1 minus 1 minus 1, 1. And so the eigenvector is 1, 1. And when lambda 1 is, sorry, lambda 2 is minus 1, this equation becomes minus 1, minus 1, minus 1, minus 1. So the eigenvector is 1 minus 1. Great. So the homogeneous solution YC is going to be C1 e to the t 1, 1 plus C2 e to the minus t 1 minus 1. Let me make sure you can see that. That looks good. And so now, since I've added on a new, a constant vector, I know what my solution in general should be. Should be this characteristic solution just found plus the equilibrium. Great. So let's see. We found an equilibrium. We found a solution. And the question is it globally asymptotically stable or unstable? So we have an eigenvalue with a positive real part. Since lambda 1 is equal to 1 greater than 0, we expect that this equilibrium is unstable, right? Unstable. Okay, and if it is unstable, which it is, find a solution so that, well, if we start within 0.01 of the equilibrium, then we can also find that the limit goes to infinity. So, just one moment. Let me just pause this and we'll finish up in just a second.